here, and it would be C prime, and you would have G prime as a conductance. Here we've got a voltage difference here, some V of Z here, and we have some I of Z here coming into it. I talked about a length here. This is a recap. A length of delta Z here in length, and there's going to be a voltage difference that's developed across here of delta V here, and there will also be the current that will shunt through these two elements right here, and that will be the actual delta I. You all remember this class? How many remember at least that bit? Right? Okay, so I'm going to go through this, try to bring you up to speed on why I'm doing this too. So from this, I fashioned two equations. The first was that the rate of change of the voltage with respect to Z, and we are in the phasor domain here, was equal to minus R prime plus J omega L prime, because we're going to work in the phasor domain, so this impedance becomes J omega L. I might as well put it down here. And by the way, this conductance becomes, or I should say, yeah, its conductance would be equal to J omega C right here. And when you do that, you got this times I. And then that's the first one. The second equation that would go along with this is VI dZ is equal to minus, it would be G prime plus J omega C prime times V. You all remember these two, right? And you know how to get them. It's just going through the motions. The voltage drop across here is R plus J omega L times the current. And that would be actually the delta V with respect to Z. The amount of current that flows here is just going to be equal to V times G. G is like 1 over R. And it's going to be plus J omega C prime times V. Then we get one equation with one unknown. Last time I only did the voltage. This time I'm going to do voltage, and I'm going to do the current equation. For the voltage equation, when you take these two things, you take a double derivative of that, second derivative of V with respect to Z squared, and now I get minus R prime plus J omega L prime, and then it's times di dz, right? You all remember that? What did I do with di dz, anyway? Say again?
Plug in.
Plug in what? You're right.
Equation 2.
I took 2 and I just replaced that, so I get one equation with one unknown. Y'all follow me, class? And I'll put that up here. So this will become the second derivative of V with respect to Z squared is equal to, and here it's going to be R prime plus J omega L prime times G prime plus J omega C prime. And it's going to be times V. V is a function of Z only. It's a phasor, so we suppress E to the J omega T. Now, at this point, I might as well just reintroduce that constant gamma, which is alpha plus J beta, and that's equal to the square root of R prime plus J omega L prime times G prime plus J omega C prime. I hope you can all see that. And that's called the propagation constant. This is from the last lecture. Alpha, the attenuation constant, Napier's per meter, and beta is the wave number. I'm going to remember that. Okay, I'm just going through, trying to go through quickly. Now, this equation can therefore be rewritten as second derivative V with respect to Z squared. And if we put gamma in, gamma squared for this term, you get minus gamma squared V equals 0. And the solution is V of Z is equal to some V0 plus e to the minus gamma Z plus some V0 minus e to the gamma Z. I'm going to talk about this today, but I'm going to do another equation with I before I do it. This we will see is a wave traveling in the plus Z direction. This is a wave traveling in the minus Z direction. You'll see that in a second. Okay. I didn't do that last time, but I'm going to explain why in a second. Now, also, what we can do with these two equations, and I'm going to do it here, so you can see it, I can get a single equation for I, which will be identical in structure to the last one, except the only difference will be V will be replaced by I. Now look at these two equations. What if I take a double derivative, or another derivative of this? I want you to just follow me on this, class. Take another derivative of that, Now I get the second derivative of I with respect to z squared is equal to minus g prime plus j omega L, or C prime, right? And then it's going to be times dv dz, right? And here I replace dv dz with this. Now I have a single equation in I. It is identical in structure. So now I have second derivative of I with respect to z squared is equal to, the minus goes away and I have g prime plus j omega c prime times r prime plus j omega L prime, and it's times I. That is gamma squared as well. You all see this, class? Identical. So this becomes second derivative of I with respect to z squared minus gamma squared I equals 0. Everybody follow me? Now I come over here, I can say that would lend itself to a solution identical in form, except I will now replace v. So now I get I of z equal to v0, or I0 plus e to the minus gamma z plus I0 minus e to the plus gamma z. This will dictate a way you travel in the plus e direction, this in the minus e direction. I'm going to show you that next. I'm going to do it right here. I know I'm moving a little quick, but I'm just going through the motions of what we did last time. Y'all remember this? All right, so now if I take this equation and I want the time domain form, do you remember how I got the time domain? That's phasor, right? We're assuming it's in the j omega domain, if you will. How did I get the time domain? Anybody remember this? Anybody at all? Yeah. You can look at your notes if you want, but if you remember it, you need to remember this. Go ahead.
You have your magnitude times the cosine. And
all right. What he's about to say is, if I want to go to the time domain, I had the phasor domain. I say v of zt would be the real part. Now that is just taking the real part of quantity. If you got a j there, anything times j is neglected. Real would be like a cosine, sine, just by itself. You all follow me? So it's going to be the real part of e to the j omega t. So we're reintroducing the variance with e to the j omega t. And then it's times the phasor form. The phasor form would be what? v0 plus e to the minus alpha z, e to the minus j beta z, plus, let me erase this. I need a little more. It's going to be this times v0 minus e to the alpha z, e to the j beta z. Now, if you take a look at that by itself, it doesn't mean a lot. Focus in on just this part of it for a second. If you look at this and you take the real part of that, so I have v0 plus e to the minus alpha z. Now I'll add the exponential quantities that the e is involved with, and I have e to the j quantity omega t minus beta z. Obviously I can do the same over here, but I'm going to neglect that for a second. Does everybody follow me how I group things? I'm going to say this right here. Can you see it in the back, by the way? You understand the only thing I'm doing is grouping the exponentials that have the j in. Now, when I talk about the real part of anything, and I'll do this over here, what do I mean? Well, first, you remember me doing this. E to the j theta was equal to cosine theta plus j sine theta. How many did? What's that called, guys? Anybody? Say again. Euler's identity, E-U-L-E-R-S, right? Euler's identity. It's critical you know this. This is one form of it. I'm going to put all three forms. The second form is, if you remember, is cosine theta is e to the j theta minus, or plus e to the minus j theta over 2. And the third is the sine of theta is equal to e to the j theta minus e to the minus j theta over 2j. These are all forms of the same thing. Do you all remember this? This has to do with a unit circle. The way you get it is if you think about a real axis and you take a look at an imaginary axis right here, this would be the j-axis, and you have a vector of length 1 with an angle theta, and you want to render it any which way. Well, this has a length 1 here. So you could say it's going to be the cosine of this angle would be the component on the real axis here, and the sine of the angle would be the component on the j-axis. That's all the first thing does. Do you all see this, class? And then you can go about getting either sine or cosine by projections, and that's really all it is. Okay? How many remember Euler's from your math courses? You should have seen this a lot in math, by the way. If you had differential equations and integral calculus, you probably saw this in a variety of different ways, but this is important. It's just one of the many things we use. By the way, what is J fundamentally defined as in mathematics? Anybody? Or I? They use I over there. What is it? Square root of?
-1.
-1, something that makes no sense, right? That's one of the things that we use, though, because we can manipulate things by using it. Anyway, back to this. Now, I want you to just follow me. This is v of zt, right? Now, look, I only put this down here. It's the real part. Means it has to not have a j. No j. If I look at this, v0 plus is strict positive. E to the minus alpha z, alpha is a strict real number, is strict positive, right? So this is going to be v0 plus e to the minus alpha z. I did this last time. Now I've got that crazy e to the j omega t minus beta z. That's an angle. That's like that theta. That would be cosine of omega t minus beta z, right? Plus j sine of omega t minus beta z. Does everybody follow me on that? The real part is just the cosine. How many see this? All right. Can you all see it in the back? Yeah, all right. I mean, you guys see this and understand it, right? So this is just going to be cosine of omega t minus beta z. We'll get to this in a sec. Now, if I wrote down this, which is the negative traveling wave, here, and multiplied by e to the j omega t, and took the real part, I would get this. The minus indicates it's a wave traveling in the minus direction. It would be e to the alpha z, because now if it's going in the negative direction, this would start decaying the further negative I got. And it would be times cosine here of omega t plus beta z. And that's the time domain form of v of zt on a transmission line that we're studying. You all follow me? Now that's all of it. Some of these things are unknown. But I want to take a look and see how we know one way, or one term is propagating plus, the other minus. Some of you remember this. When I looked at this right here, that dictates an angle. Do you all remember that? So if I look at this and I say an angle is equal to omega t minus beta z, and then I talked about a wave on the ocean. Do you all remember that? If you have a wave on the ocean, at the peak of the wave, the phase, if it's a cosinusoidal variation, and ocean waves approximate that, then the peak of that wave would be a constant phase point. Do you all follow me? A surfer would be just in front of that if you wanted to go forward with that wave. So what we want to do is how fast that phase is traveling. It means we'd like to see the derivative of this with respect to t and set it equal to 0. We want to see how fast the actual constant phase term changes. We take a derivative of this with respect to t, we set it equal to 0, and we get simply omega minus beta times dz dt. Now dz dt is just like dx dt, it is a velocity. Y'all follow me on this, class? That's called the phase velocity because we're tracking the phase of the wave, or the angle of the wave, how fast the constant angle moves. From here, you can see that we get phase velocity equal to, and just take the omega to the other side, it's minus omega, then divided it by beta, and that's equal to omega over beta, and that is dz dt. Now, how many see this is positive, right? The wave is traveling in the positive direction. If you would go ahead and plot what I just have right here, and you would increment z and t, and just make a movie of it for different t values, you'd see that wave crest moving off to the positive z direction, all right? Now this one, on the other hand, you would see moving in the other direction. Okay, and this is basic wave motion. You had this in physics already, probably several times in different ways, but I'm just stressing this, that that's how you get the actual phase velocity. Okay, now wavelength, now I'm going to go over here and do wavelength. I didn't do wavelength last time, I don't think. I looked and I didn't see it. So we're going to do wavelength and we're going to do period too. And I think then, got two more things to do and we'll do some problems. All right. So now the next thing I'm going to do is talk about wavelength. So the symbol for wavelength is lambda. What would be in meters? And what does wavelength mean? Well, here's how we do wavelength. I say we freeze the actual time. So I'm going to let t equal 0 here. And I'm going to plot just the positive going portion of the wave here. But I'm going to do something else. I'm going to assume it's lossless, or alpha is 0, just to make things easy. If you look at this, now I have an equation here that's just v0 plus, and it's going to be cosine. Remember, I'm making t 0, so it's cosine of minus beta z versus z. Can you all follow me on what I'm doing? I let t equal 0, so the omega t goes away. Now I let alpha be 0 to make it simpler, or else I'll have decay. And if I look at this, I want to plot this versus c. Now, how many know a cosine function is an even function? Raise your hands if you do. You know what an even function is, people? If you had math, you should, your mathematics courses. Even means the value of that function is independent of the sign of the argument. Cosine of minus x would be cosine of plus x, right? That's an even function. Odd function is cosine, or sine, for instance. The sine of x is minus the sine of minus x, right? It's an odd function. That's an even function, and because it is, we can get rid of this. Do you all agree with that? Now, if I plotted that versus z, what I'd see is this. And I think everybody has a fairly good handle on this. The actual distance over which a wave repeats itself, if it's periodic, is called, technically, if it's versus the positional variation z, it's called the wavelength. This is the wavelength, okay? Now, just hear me on this. I want you to just see this, how simple this is. When I look at this point is z equals 0, right? So cosine of 0 is 1. That means the height here is v0, right? You all agree with this? Well, keep going. Cosine waveform goes 0, right? It's 0 at 90 degrees, right? Or pi over 2. Then it's going to be minus v0 at what? 180 degrees, so pi over, or just pi. And it keeps going until it hits here. And at this point, I know that argument beta z is 2 pi. Do you all agree with that? Now, that's the point where the wavelength is defined. So here, we're going to have beta times z. Z is the wavelength is equal to 2 pi, or the wavelength itself is simply 2 pi over beta. And that's the fundamental definition of wavelength. Do y'all follow me in the reason for it? We got phase velocity, we got wavelength, both critical. Everybody with me on this? And when you work problems, this will become very clear to you, because then it reinforces what you've heard. You force yourself to make sure you understand the theory. Now we're going to do the same thing here, but instead of freezing time at 0, we freeze the position at 0, z. Okay? And this is called the period of the waveform. You have probably a fairly good handle on this, because you've had circuits. All right, so next. This is going to be the period of the wave. The symbol for period is t. It just means the time over which it repeats itself. So here, go back and I do the same thing, only now I plot it versus time. And here I let z equal 0, alpha equals 0. We're only going to take a look at the positive going portion right here. This is the only thing we're going to look at. We don't care about the negative because it'll just complicate things and it's just going to be redundant, the information we get from it anyway. So if we plot this, we're going to plot v naught plus cosine of omega t, right? Same exact thing we did before, right? I don't even have to make the argument of an even function. Now what happens here? Does this, does it? You all agree with that? Isn't that a cosine waveform versus? This is the distance over which it repeats itself, right? That's the period in the time domain. In the spatial domain, it's wavelength. Here it's the period. How do you get the period? Think about what I did before. Well, I know what? At this point in time, the omega times the period is 2 pi. Y'all follow me? That is going to start again. 2 pi radians at 360 degrees. Follow me, class? And that means, what is this? The period itself is going to be simply 2 pi over omega, something that will stay with you. What is omega in terms of f for all those who had circuits? 2 pi f, you're almost afraid to say it. It's just 2 pi f. So 2 pi over 2 pi f is 1 over f. And this is critical, that when you have something at a constant frequency, then the period is inversely proportional to the frequency. T is 1 over f. So if it's 60 hertz, the period is 1 over 60. That's all it is. All right? But it's important to have an appreciation of this. So now we've covered wavelength, phase velocity, period. Now, the next thing, and I showed you the equation for I, right? Now we're going to talk about something called characteristic impedance that were part of the problems I gave you, but I told you you had to read them. How many looked at the problems? All right. There are things in there that are going to be very clear and evident to you very shortly if they aren't read. It's not hard stuff because you have all this basic theory from circuits. Let me get rid of this. I don't think there's any rain today, is there, class?
No.
I hope not. Because when there's thunderstorms in this room, I can hear the thunder, and I hear the rain hitting the ceiling. Have you ever been here in this room for a thunderstorm? Or that room? And it's annoying sometimes. But anyway, back to this. So now we're going to go ahead and we're going to talk about characteristic impedance. So we start, and I'm going to start this way. Remember that I had dV dz is equal to minus r prime plus j omega L prime. We're going back to that differential model times I, right? Now, I'm going to do this for just the positive going portion of the wave. So if I take a look at just wave moving in the plus z direction, I know my v of z will be equal to some v0 plus e to the minus gamma z, and my I of z is going to be I0 plus e to the minus gamma z. I'm just making sure. We're going to stay in the phase in a minute. Those are the two components for the positive portion of each wave, all right? Now, if I take a look at this, and I take this equation, well, what is dV dz? Well, that would be minus gamma v0 e to the minus gamma z. Can everybody follow me on that? Just take a moment. Make sure you do. I'm going to take a derivative of v with respect to z. We just bring out the minus gamma. So here I get minus gamma here, v0 plus e to the minus gamma z, and that would be equal to minus r prime plus j omega L prime times I. I is equal to I0 plus e to the minus gamma z. Please just take a look. Make sure you see this. There's nothing I'm doing that's in any way tricky. I'm just doing the derivative, and going ahead and putting in the values I put down here for I and Z into that equation. Now if you look at this right here, one thing, and I'll do it this, what do you notice happening? First of all, can I simplify it in any way, shape, or form? Class? What about the negative sign? Can we get rid of that? Don't they appear on both sides? Sure. Now, you guys are fairly smart. You know about the last thing you want to do is carry things through. You don't need to. What else can I get rid of? Just take one. That's right. This appears on both sides, so divide it out. Now I have this. Remember, I mentioned characteristic impedance. Anytime you think of impedance in circuits, you think of a voltage divided by a current for a given element. Y'all, isn't that right, class? So if I go ahead and I define V0 plus over I0 plus, this is called the characteristic impedance. Of the transmission line. The symbol that we use is usually just Z naught. It'll be some form like that, but it'll be clear by the use of it. It's an impedance, the characteristic impedance, a ratio of the magnitude of V to the magnitude of I on a transmission line. Now, look at this. Here's V0 plus. If I divide it by I0 plus, and then divide it by gamma, right here, now I have this. The only thing I did is manipulate it to get it in the form I can stick in here. You all with me? So what is this? Well, it's equal to R prime plus J omega L prime over gamma. Now, I'm going to go ahead and put gamma back in there. I erased it over there. But remember, gamma is just the propagation constant. Correct, class? So this becomes R prime plus J omega L prime over the square root of R prime plus J omega L prime times G prime plus J omega C prime. You all follow me? Now again, the only thing I've done is taken gamma and stuck it in there. What do you see happening to that R plus J omega L prime? I can simplify this, right? This down here is what? R prime plus J omega L prime to the 1/2, that's the same thing as the first power. So what I can do is this, and this is the way you're going to see in the text. I can write this as simply R prime plus J omega L prime over G prime plus J omega C prime. And that, in fact, is the characteristic impedance of the line. You'll notice the characteristic impedance is defined in terms of the ratio to V0 plus to I0 plus. If we would get the ratio, and this is important, I'll star this one. If we got the ratio of V0 minus to I0 minus, the same thing, only it would have a minus value, be minus R prime plus J omega L prime over G prime plus J omega C prime. It would have a minus sign there. By the way, one of the things I typically do is circle any minus signs, because sometimes I think I scratch the paper, but if I circle them, I know that's a minus sign. That's what I take a look at this. So really what this is minus the characteristic impedance, Z naught, that I've defined here. Now keep that in mind. You understand that, class? Now we're going to rewrite two equations. Most of that, except for this right here, was rehashed. All right, I wanted to make sure I brought you up to speed, didn't leave you behind on anything. I just gave you a little review. Now, the next thing we do, this is important. Now we're going to use that concept of Z naught. By the way, that doesn't change versus position on the line. One thing about a transmission line is the cross-sectional area and electrical parameters do not change versus distance. That's very important. There are things called balloon lines and stuff. That dang thing is annoying. Leave it on for now. Matter of fact, well, one second, I want to turn off that projector. That was off. All right. So, now we go back to the equation. We had V0 plus, or V of Z was equal to V0 plus e to the minus, and here I'm going to put it as minus alpha z times e to the minus j beta z, and I can put plus V0 minus e to the alpha z, e to the plus j beta z. This is in the phasor domain. And I can write Iz here in terms of V0 and in terms of characteristic impedance. Instead of putting the I0 there, I put V0 plus over Z naught times e to the minus alpha z, e to the minus j beta z. This is the important one. Remember I said the ratio of V0 plus, or V0 minus to I0 minus was negative Z naught? You all remember that? What that does is make this next term negative. Circle that. It's going to be minus V0 minus over Z naught times e to the gamma z, e to the plus j beta z. Okay, those are the two equations that are going to dictate behavior on the transmission line for V and Z in the phasor domain. Now come back over here. Yes, fun. I'm going to go to those in a second. I'm trying to do these in the way that Whitmore's book does it. Next, I'm going to talk about power. I didn't talk about power flow last time, did I, class? What do you know power is in general? Think of circuits. Simplest form in your own words. Anybody? You've got voltage and current. What do you do with the two to get power associated with an element? Multiply, right? And generally speaking, there's two kinds of powers that you talked about. There was instantaneous that was in the time domain, right? There was V of t, I of t. Then there was the average power, right? Related to the RMS voltage and current. And generally speaking, when you had average power, and here's the way I'm going to do this, just consider power for a wave traveling in the positive z direction. If we do this and we have to include negative and positive flowing power, it's a long mess. But I'm going to try to just get to the point. You'll see the parallel. So positive z, that means V of z, right, is V0, right, plus e to the minus gamma z times e to the minus j. Beta z, I of z is equal to V0 plus over Z0. Now z can be complex, so I put magnitude of z here, the characteristic impedance, e to the j theta, the angle associated with the characteristic impedance, and it's going to be e to the minus alpha z, e to the minus j beta z. Just go with me on this one. Do you all agree that z, for instance, because the characteristic impedance, maybe I can put it here, that characteristic impedance is equal to the square root of r prime plus j omega l prime over g prime plus j omega c prime. Can you all see if r and g and l and c exist, you have the possibility of complex numbers, real and imaginary parts, or magnitude and angle. Do you all see that, class? Now, I might as well add this right here. If you have a lossless transmission line, a lossless T line means R prime equals G prime equals 0. There is no resistance there to dissipate power. You all follow me? If there's no resistance or conductance there to dissipate anything, then the characteristic impedance becomes what? You all see if R and G goes away, then the J omegas cancel, right? And you get this. It's the square root of L prime over C prime. That is what you actually read off any kind of information about your coaxial cable that comes from like Spectrum or Cox Cable or Verizon to your house. The coaxial cable will have it's typically 75 volts for any carrier that's from the street to your house. Now, any kind of microwave engineering, or I should say high frequency engineering we do, typically has 50 ohms. The cabling is 50 ohms. From the house is 75. Has anybody ever cut open a coax cable here? Have you put in a splitter? You know what splitters are? They take the signal and they divide it. All right, well, if you did that, then you notice one thing about the coaxial cable. It had about a solid copper center that's bendable. Then it was surrounded by insulation. It's like a white plastic insulation. And then it had a braided shield on the outer part of the coax. And then it had a black thing around there that's really material just prevent it from abrasions and critters chewing on it, stuff like this. And it's very bendable. Okay, I'm mentioning this for a reason. Now, coax cable, you can bend it a fair amount. You can do splitting with it easy. There's another thing that you'll be in, and we'll talk about, and you'll see more of later, and that's called fiber optic cable. Now, real fiber optic cable is actually glass. It's silicon dioxide. They have DuPont and Dow Corning, they put impurities in there, enough impurities so it's flexible to a degree. But that stuff is not truly a transmission line in the true sense. The only thing it's doing, it's a waveguide that bounces photons around. It doesn't have current flowing in it, and it's a lot harder to work with. I just want to mention this. The benefits of that is it has an enormous amount of data you can throw through there. Maybe 10 orders, right? About 8 orders of magnitude more information per second can go through fiber optic. It has much, much less attenuation. You're going to see something in a second where the attenuation for typical kind of coax cable at about 100 megahertz is 4.5 dB per 100 feet. Not that bad, but it's such that the signal's dropping, and after about 200 feet, you have to take that signal and re-amplify it. It's called a repeater stage, and you need to do that if you're going to use just coax cable. You don't have to do that with fiber optic, not for 20, 30 miles. Anybody here ever work around real fiber optic cable? Stuff they bury in the ground? All right, you know what I'm talking about. You can really mess that up. It's very hard to fuse together when you break it. But, well, nowadays they have technologies that allow you to do that. I don't work with real fiber optic very often. I'm around it. I have to deal with after they pull the signal off the fiber. Okay, so that's the characteristic impedance of your transmission line that goes to your house. Next time you look at it, see if you can find 75 ohm on it. How many have cable to go to your house or your apartment? I guess some of you don't, which is rare, but because almost I think they still have cable around here, right? Buried cable everywhere. Even Verizon with its fiber optic backbone still brings it in with a coax cable. So you're an electrical engineer. You should at least experience what you're probably going to see all the time in the real world. Go take a look at it, see if it is at 75 ohm. Is there anybody aware of any other value for that, for coming off the street? I think it's always 75. Pretty sure. Anyway, that's what they mean by this. The ratio of LSC, by the way, has nothing to do with the inherent resistance per meter of the stuff, as some people mistakenly think. It is actually a ratio of the square root of L over C. All right, now, back to this thing. We're talking about power. So average power, back in the day when you had circuits, do you remember this equation? 1/2 the real part of V times I conjugated. You all remember that? How many do? All right. Now, what does I conjugated mean, or what's a conjugate? Let me ask you this. If I give you I is equal to 5e to the j 45 degrees, what is I conjugated? That's supposed to be that. Anybody? What does conjugation do? It's one thing, it's very simple. It will, it will absolutely, it will invert the symbol, the degree sign. Basically, this will become 5e to the minus j 45 degrees. All right, that's all it does. And if you had, for instance, I equals 1 plus j1, I conjugate would just be 1 minus j1. That's all it does. It flips the sign on the angle. Y'all with me? Now, this is the fundamental definition. I'm going to remember that definition from circuits. You had it, right? You had to have it. How many had Dave Irwin? Oh, I was here. If he saw you didn't know that. Who's your name? Anyway, coming back to this thing. He's a stickler for circuits. So, like Ohm's law. If you don't know Ohm's law, oh, God help. Anyway, coming over here, let's do this. And I want to make one point here. Now, you see how I put this as magnitude of Z, and I have the angle here downstairs. Y'all see this, class? What happens if I want this angle upstairs, or the numerator? just take that angle and make it minus. You all remember this class. So I'll just go ahead and I'll do it right here. I'll make the angle e to the minus j theta, and this is associated with the impedance. So now back to this. Power is 1/2 the real part of v. Well, there's v right there, so I can put it in v0 plus e to the minus alpha z. Make sure you write this down. E to the minus j beta z. Now I've got to take this and I conjugate it. You all hear me? When I conjugate it, v0 doesn't change. The magnitude of z doesn't change. E to the minus alpha z doesn't change. These two flip sides. So now I got v0 plus over magnitude of z0. Then I have e to the minus alpha z. But I have e to the plus j beta z, and I have e to the plus j theta associated with the impedance z. Can you all see this, class? Everybody? Okay, keep watching. When I go through this, I want you to just follow this. The 1/2 isn't going away. I have v0 times v0, and I just want the real part, that's strict real, v0 plus squared. I have z0 magnitude, that comes out in front, right? Now, look. I have e to the minus alpha z, e to the minus alpha z. That's e to the minus 2 alpha z. Do you all see that, class? So I have times e to the minus 2 alpha z. Now I have e to the minus j beta z times e to the plus j beta z. What is that? What's e to the j times e to the minus j? E to the 0. What is e to the 0? 1. Do you all see that? That's 1. These two go away, basically. Then I have the real part of e to the j theta z. What is that? What's the real part of e to the j theta, period? Cosine. Y'all remember when I had that stuff up there, right? It's simply equal to the cosine of the angle associated with the impedance. And this is the average power flow. And power flow is in watts, by the way, right? We use average most of the time. Got to mention something. Anytime you look at this thing, one thing to take note of. If it is lossless, then that term goes away. Alpha will be 0. If it is lossless, there will be cosine is 0, which is 1. So the power flow would just be 1/2 v0 squared over z0. That would be the power flow if it was a lossless case. Y'all with me, class? All right, while we're at this, we did, that's me. We did, that was thunder for a second. We did the actual wavelength. We did phase velocity, right? But if we were going to use L and C, what would the phase velocity be? This is sort of an added. Well, it's omega over beta, right? Now, I'll tell you what. Let me back up for a second. We can get beta easily from the propagation constant, which is alpha plus j beta. But if it's lossless, you might as well finish my thought here. If you think about the propagation constants, alpha plus j beta. Now, I'm going to do this, and I'm just going to say this would only be for the lossless case. For the lossless case, R is 0. So you have j omega L, and then you have j omega C. This is prime. All right, that means this is j omega square root of LC prime. You all see that, class? That would be the propagation constant if it's lossless. You'll notice it's just j times omega square root of LC plus 0. Alpha is necessarily 0 if it is lossless. Are you with me on this one, class? How many see this right here? It must be. That just tells you it's lossless. All right, this is beta. If that's beta, when I take omega over beta, I see that the phase velocity is just the square root of L prime over C prime. And that's true if they gave you an L and a C per meter, you could get the phase velocity. And it will never be greater than the speed of light. for a transmission line. You all with me on this class? If it ever is, you did something wrong, or somebody lied to you. All right, I got that down. Now, next. This is always one of those fun things. Do you have a problem that you'd like me to do? I miss doing problems today. Any problem at all? If not, I want to just finish one thing, and I know I've got about 2 minutes, 3 minutes actually left. And I'll try to do one as soon as I'm done with this next one. So far we're just talking in generalities about propagation on transmission lines. They're not a finite length. We all know that a transmission line is going to be terminated into something called a load. So if you have a transmission line as such, it's got a characteristic impedance of Z0, and it has some load. All right? The way they do business here, to make things simple, they're going to say, we're going to use this as the Z-axis. We're going to say we're going to put the load at Z equals 0. That's just the way we do business. Now we're going to assume the transmission line has a certain length, right here. And we know the equation for voltage and current on this transmission line. Real quick, V of Z in the phasor domain is V0 plus e to the minus gamma Z plus V0 minus e to the plus gamma Z. And I of Z is equal to V0 plus over Z0 e to the minus gamma Z minus V0 minus over Z0 e to the plus gamma Z. Now I just recreated the stuff I kept writing before. You all with me? If you're at the load, if you're here, so if you are at Z equals 0, right, then V of Z becomes what? Well, if you're at Z equals 0, the e to the 0 and e to the 0 here is 1. Can you all hear me on that? So this means that's V0 plus V0 minus. And I'm going to go ahead and divide that by I of Z. But this is at Z equals 0. And that means it's V0 plus over Z0 minus V0 minus over Z0. You all see what I'm doing here? But what is that value? What is the ratio of voltage to current if you're at the load? ZL. You all see that? You're measuring the voltage and current at this point. It is across the impedance, ZL. So that's ZL. Right here. Now, by this time, this would be ZL. And I'm a little short on time here. I got this equation. If we manipulate that, we can get the ratio of V0 plus to V0 minus. You see that there's V0 plus, V0 minus there. This is called the reflection coefficient. I'm going to put it right here. So the reflection coefficient. Symbol is capital gamma, and that would be equal to V0 minus over V0 plus, and that would be ZL minus Z0 over ZL plus Z0. And that puts me almost out of time. I think I got maybe a half second. Now, you can take that value of gamma and rewrite these two equations. I'm going to put that on OneNote. I'm going to give you some additional problems to do for Monday. On Monday, I will do problems, but I had to get this theory out of the way before I really go into the problems. And I'll give you some homework to do. If you're a good student, you want a good grade in this class, like an A and stuff, do the homework, keep up with it, and come with your questions. Now, I warn you about one thing. Lots of people fail this class. I hate to say it, they do. And the reason they do, in my opinion, is they wait until the last minute to study for the quiz, like every Thursday night at about 1 a.m. And they wait for the test, the day before the test to study. And they're very interested in other things. And I know football's here and all this. I warn you, even some of the brighter kids have failed this course for one reason. They weren't attentive early. This stuff, everything builds. I'm just warning you. What we're covering today, we're going to use for the rest of the semester pretty much. And more and more and more stuff is going to be added. And you have to keep up with it. You can't. I think maybe there's some super bright kids. If you try cramming, you probably could kill yourself. And that happens. I see so many kids. I hate to see that too. Get a lot of A's, and unfortunately, a lot of F's.